Basically, we wanted to talk about machine learning because we felt like there weren't enough talks being done on machine learning and wanted to add to the pile. And so my name is James Jun. I'm one of the senior product managers in EC2 and managing some of our GPU compute instances. And at Amazon, we have this notion of working backwards from customers. So we'll look at customer experiences and their workloads, some of the challenges that they're facing, and try to figure out how to provide an adequate solution for them. And so today we've invited our friends from Facebook to come and talk about some of the machine learning workloads that they're using, some of the challenges that they have with, obviously they're a big scale with their billions and billions of active users. And then we'll kind of talk about what trends we're seeing in machine learning and some of the infrastructure that we've built to go and support some of these large-scale workloads around machine learning. And then we'll talk about some of the enhancements just from compute, networking, and storage, as well as talk about inference as well. So with that, Maxim is a research scientist at Facebook. He's been involved with deep learning, numerical methods, and parallel algorithms for over a decade at companies like Facebook, NVIDIA, and Intel. So with that, I'll have Maxim come up.
Thank you for the introduction, James. Welcome to the talk. I appreciate you guys coming here. I will talk a little bit about the challenges and opportunities of architecting AI systems at data center scale. I hope you learn a few new things here about our workloads, and maybe you'll use that information. It becomes useful for you as well. So first of all, I wanted to kind of delineate the differences between artificial intelligence, machine learning, and deep learning. Those words are sometimes used interchangeably. We use the AI in the title, but we really will be talking about deep learning models here. So artificial intelligence refers to programs with the ability to learn and reason like humans. Machine learning is a subfield of AI. It's a set of statistical techniques that enables machines to improve with experience. And deep learning is really about using multi-layer neural networks to learn from vast amount of data, right? So we will be talking mostly about deep learning models here. How does the world look according to deep learning? Well, this is a plot that some of you might have seen before, but this is a plot of deep learning research over the last 30 to 40 years. We see that there was some interest in deep learning in the early days, but it was kind of slowly growing, not very much. There was a big bump in 2012, and then there was a double exponential growth after that. So what happened in this bump here? What triggered this exponential growth? Right at this point, there was a network, deep learning network that was proposed called AlexNet. It was proposed for the ImageNet challenge, and it won that competition by leaps and bounds, something that people could not have done in previous years. It generated a lot of interest because people felt that this type of technique could be applied to other fields as well, and they wanted to see what happens, how does it work, and so on, and this led to this exponential growth. So how does deep learning compare to other methods? Well, first of all, let's try to look at some hypothetical curve before we look at the precise examples. If we plot accuracy on the vertical axis, and we plot amount of data and model complexity on the horizontal axis, we'll see that many common machine learning methods, they work well when, or work better than deep learning when there is few data points available, little data, and there are not that many parameters in the model. This is the left bottom part of the graph. However, as more and more data becomes available, the statistical performance of these methods doesn't increase as much, while deep learning statistical performance continues to grow more and more with the amounts of data and complexity of the model. I also wanted to point out, and you'll see this throughout the talk, that as you increase data and model complexity, you also need to provide the hardware resources to train these models so that they can achieve their best potential. So now let's look at a concrete example. This is a Facebook computer vision deep learning model called ResNext. Many of you might have heard of it. It's open sourced. And this plot here shows the complexity of the model on the horizontal axis, and it shows the accuracy, the statistical performance of the models on the vertical axis. There are two curves here. We'll first focus on the gray curve, okay? So we take this model, and you'll see different points on this curve. These are different configurations of the model. But as we go towards the right, the model becomes larger and larger, more complex. And we see that the performance of the model on this task improves, as we have indicated in the previous plot. If we take the same model and then rather than taking the ImageNet data set to train it, we train it on Instagram images, about 1 billion images, but then we still use this model to make predictions on ImageNet, we'll end up at a purple curve. So more data that we used resulted in the model being even more accurate. And the more complex model, the further accuracy you get. Now I wanted to show you a general machine learning pipeline. This is very typical at Facebook. And I wanted to discuss some of the characteristics of this pipeline and how it has grown over the years. So first we start with the data, right? We have some warehousing of the data. We preprocess this data to extract important features that will be inputs to our models. We train the model. We evaluate how well it is doing. And based on this evaluation, we might take some decisions. We may modify the features that we are feeding to the model. We might decide to make the model more complex. We might change the characteristic of the model. We need to experiment a lot with it. But once we are satisfied, we are actually able to then deploy the model to make predictions. So let's focus on the growth in each of those areas and how it has come over the years. If you look at ML data growth, this is how much data, percentage of data is used from all the data in the warehouse for machine learning pipelines. In 2018, last year, it was about 30%. This year, it's 50%. So the percentage of the data used for machine learning, deep learning has increased. Moreover, the amount of data in the warehouse has doubled. So overall, there was a growth of about 3x in data used for machine learning. With respect to training and evaluation, we also see tremendous growth. For example, if you look at ranking engineers that Facebook has, we have twice as many. If you look at workflows that we use, there are 3x more workflows. And proportionately, the compute for those workflows has increased by 3x as well. And with respect to deployment and predictions and inference, we do roughly 400 trillion predictions per day. We do 6.5 billion translations between languages. And what is also important, many of the deep learning models help us remove fake accounts from Facebook website automatically so that people can feel safer online. Now I wanted to show you that this machine learning pipeline doesn't come for free. It relies on many system and hardware resources, and it really strains those resources. So for example, storage resources are used for data and feature extraction. Networking is used all over the place. Compute and memory is used in training and deployment. To make matters worse, as we want to have more complex models, more data, we see that if you look at the processor performance, the growth in the performance have slowed down over the years. This is a plot of essentially how much time it took to double the performance of the processor. We see in the beginning that it roughly took, say 2 years to double the processor performance. From 2005 and on, it took 3.5 or more years, 6 years. And now we are at a point where we expect 2x to come in 20 years. So while we have a high need for our performance and resources, the growth in performance is actually kind of came to a halt, and Moore's law has declined. We see that the solution to that is to do hardware and software co-design so that you optimize your software and hardware systems for specific workflows that we have. And what are those workflows? So there are three main directions that we are concerned about. One is ranking and recommendation, which is used in news feed and search. Second one is computer vision, which includes image classification, object detection, and video understanding. And finally, language translation, speech recognition, and content understanding. Those are all very important to us, and they constitute the three main workloads. This is a slide that shows how much capacity in the data center those workloads use. And this slide might surprise you, because many people focus on computer vision models and language models. And you can see that for us, relative to language models, ranking and recommendation takes up 100x more capacity. Computer vision, with respect to computer vision, it's 10x. But the main takeaway of this slide, and I think this is something that not many people kind of are aware of or focus on, is that recommendation models are among the most important models that run in a data center. So what are now that we know the workloads, we know our models, what are the characteristics in terms of operators of those models, in terms of compute? How is it broken down? So this is a plot of different common operations that models perform across training and inference. Yellow part of the plot corresponds to matrix-matrix multiplications. It's about 40%. Red part, which is 4.4%, are convolutions. And I wanted to point out that some of the convolutions belong to the yellow part, because if you have irregular filters or strides, those types of convolutions are often not optimized directly, but rather converted to gems, and gems are used to run them. So overall, for convolutions and gem, we have only 45%, and many people are optimizing those operations, but they're not even the majority of operations that run in many of the models. We have about 8% of operations in embedding lookups. Those lookups are used for language models and recommendation systems. We'll see an example later on. And then we have tensor reshapes and a long tail of all kinds of random operations that each model might have on its own. So what I would say to the people who are looking at systems and hardware is that you shouldn't just optimize your convolutions and gems. It's very convenient. It's kind of easy to focus on and look at, but these are not the only things that we care about. What about memory and storage? So on this slide, I wanted to show for the three groups of workloads that we have how they map to different system resources, right? And we'll split memory into two parts. We'll split bandwidth and capacity. Capacity is the amount of memory you need. Recommendation system models are typically require a lot of memory. They're very, very big models, much bigger than any other model. They require a lot of bandwidth for the embedding lookups. They require interconnect, because if you're running in a distributed or parallel setting, you'll exercise that interconnect, as you'll see later. And they still have a relatively high compute rate, because those models also have MLPs, and they still need to finish the computation. On the other hand, computer vision has a high memory capacity, but not because of the model itself, but mostly because of the inputs. Inputs, such as video, can require a lot of memory, so you need a lot of memory to store things, but it's not the model per se necessarily. They don't need memory bandwidth, they don't need so much of the interconnect, and they have a very high compute rate, as we all know. Language models, on the other hand, require relatively high capacity. They exercise interconnect because they have many different operations. Sometimes attention, for example, may exercise it a lot. And they have a high compute rate. And what's also important to take away here is that, as I have shown you in the machine learning pipeline on the previous slide, people often iterate when they work on these models, when they design the models. So what is really important is to provide a lot of flexibility to the engineers and researchers who are looking into those problems. They want to have experiments fast, but they also want to have the flexibility for fast prototyping. So how about network? So we will look at network from a perspective of a deep learning recommendation model. I chose this example because I think that's not a common example that people show, and I think it's something that can be more insightful to people in the talk. This is a generic deep learning recommendation model that we have open sourced. It's on Facebook Research GitHub. We call it DLRM. And let's try to understand the components of this model before we go to the networking resources that it exercises. First of all, the input to the model consists of two types of features. There are dense features. These are continuous numbers, usually concatenated into a vector, just floating point numbers. There are sparse features. Those are categorical features, usually a set of integer indices, for example, that are we use to look up vectors in embeddings. Dense features are processed through a set of MLPs. These are MLPs that require your compute in this model. And sparse features, once you look up the embedding vectors, they are pulled together into a single vector and then interacted during feature interaction, and the results are fed into further top MLP. Let us now zoom in on the embedding lookup, because perhaps this is not an operation that is commonly used. And let's try to understand what it does. So we have a set of indices. Here I have shown a wide embedding table, and we are looking vectors A, B, and C. Our pooling operation is a sum operation. And the result is a single vector that is propagated further in the model. It's interesting to see that this operation can be also seen as a sparse dot product versus a dense. So sparse vector times a dense vector. If we represent the indices as a multi-hot encoding, and we multiply it with the transpose of my embedding table, I'll obtain the same result. And if I actually build many of such vectors, I'll have a sparse matrix times a tall dense matrix. An operation that's very common in linear algebra. If you wanted to run this model in parallel or distributed setting, we have a couple of choices to make. Right. So before we put the entire model on a distributed set of nodes or devices, let's focus on MLPs. We always have a choice of model and data parallelism. Here we are going to actually, for MLPs, we'll assume we are going to use data parallelism. In this case, we have two choices. We can run a parameter server and then asynchronously communicate between MLPs, or we can put our MLPs across different devices or processing units and perform an all reduce running in synchronous fashion. Let's assume we choose the latter. And let's now add our embeddings that we have seen in the model. So embeddings cannot be often put together onto a single processing unit or a node. They cannot be put together because they require a lot of memory, and there is simply not enough memory on the node or the device that you are choosing to put them on. So here I chose one embedding per node. Could be many, but there is some limited amount. And they are not replicated. MLPs are replicated here. The embeddings are different. Right? They're different on each node. So for embeddings, we essentially used model parallelism. We put each operator separately. Each operator receives the entire batch of lookups. It performs its own lookup, and then it distributes parts of the result, right, to each of the bottom processing units which have the replicated MLPs, which accept part of the batches because they're data parallel. The operation between the embedding processing units is all-to-all personalized communication. Sometimes we refer it as butterfly shuffle because it just resembles a butterfly a little bit. And the operation between the bottom MLPs is an all reduce. And it's very clear from this model that we will exercise a lot of networking here because we'll need to shuffle this element, we'll need to perform all reduce, and so on and so forth, at least in the way we map the model to our system, hypothetical system right now. So now we have done some experiments with different models on different types of systems. We have experimented with AWS system with an elastic network adapter, AWS system with an elastic fabric adapter. This is a new, kind of a more advanced version. And we also ran on our FAIR Facebook AI research cluster. It's important to note that these systems, they differ particularly in the interconnect that's used in them. AWS ENA is about 20 gigabits per second, maybe a little bit higher. EFA is about 100 gigabits per second, and FAIR provides 100 by 4 gigabits per second. And as we look at these models, these are not recommendation models, these are language models, but still, we can see that their relative performance increases as we provide more and more interconnect support bandwidth. And we also think that in the future, many of the upcoming workloads, for example, graph learning, will exercise interconnect even more, and it will become even more important. So now that we understand our workloads, our systems, our models on a few examples, as I said before, one of the critical pieces that people look for is to be able to easily experiment with them. And I wanted to take a couple of slides to talk about programmability. We believe in the PyTorch framework a lot. I think it's a spectacular framework. It's very easy to use. If you haven't tried it by any chance, give it a try. It's very natural. It provides eager graph-based execution, dynamic neural networks. It does support distributed training and accelerated inference on hardware. And the entire focus of the framework is on simplicity over complexity. It should be easy to experiment with and write your code, and things happen from there. We are also putting a lot of focus on going from prototyping to deployment in PyTorch. We want not only for you to experiment in PyTorch, but also to be able to deploy the models in PyTorch. If you're interested in more details about PyTorch, you can always go to pytorch.org for many tutorials and documentations. They have spectacular forums. You can also look at several of the models that I have described in the talk on Facebook Research GitHub or PyTorch GitHub. They're all available for you to play with. And if you want to try PyTorch on AWS, I have also provided at the bottom several links that you can try and play with it. And with that, I wanted to give the stage back to James, who is going to talk to you a little bit more about AWS and how you can work with it.
All right. Thank you, Maxim. All right, and don't worry, we're aware that the replay party is coming up, and so we'll make sure you guys aren't late for that. Just show of hands, how many people are running some kind of machine learning workload today? Okay, wow, a lot of you. And how many people are doing machine learning training that's distributed, so more than one server of GPUs? Okay, oh wow, that's a good amount. Okay, awesome. And so, not everyone can operate at the scale that Facebook has, and we don't all have large data centers like Facebook has, and so what AWS is trying to do is provide that quality of infrastructure, that scale of infrastructure for everyone else, right? And so if you look at some of the customers that are using AWS today and machine learning workloads on AWS, we have tens of thousands of customers that are already using machine learning already. And the vast majority of the customers that we do talk to are at least thinking about it and deeply investigating, how do we use machine learning? And and there may be some customers in this room that your logo is on the screen, and we thank you for that. And we want to continue to work with you and understand your feedback and continuously improve on what we're doing. But it's always great to see more and more customers. I mean, a lot of the customers here were in Andy's keynote and have really cool applications. Customers like Intuit, the NFL with sports analytics, making travel better with companies like Lyft and Expedia. And so we're really excited to continue to add and grow the amount of ML customers that we have. So here are just a few of the use cases that people are doing. And so, in the fullness of time, we expect almost every application to be infused with some amount of machine learning. But it's still early, and there's a small subset of applications that I'm showing here that I wanted to highlight. And so, in areas like manufacturing, we have customers like Formosa Plastics that are using machine learning to do better detection of defects on the production line. In retail, there's customers like Zalando that are doing, creating better customer experiences for their customers using personalization. In healthcare and sciences, life sciences, which is a really interesting area where improving patient lives is really a hugely impactful thing, and customers like Celgene are doing that by discovering new treatments and new drugs to help do that using machine learning. In travel and logistics, customers like Atlas Van Lines are doing better van capacity management and dynamic price management. And then lastly, in energy, the Connect Energy group is using machine learning to better predict future demand and supply of electricity. And so one of the main goals we have at AWS is to provide machine learning for every developer. And we know developers are all at different levels of skill set. And so what we've done with our machine learning stack is actually kind of categorize it into 3 different groups. And these 3 areas are kind of targeting these different skill levels. So if you look at that top layer of AI services, these are meant for developers that may have little or no ML experience. So they can take these services and build sophisticated AI-driven applications, such as call centers, live media subtitling. It could be understanding voice of the customer. And they can do all these things without having to build and train their own machine learning models. We have services like recognition that help with image and video analytics. We have text-to-speech and speech-to-text with services like Poly and Transcribe. People can leverage the decades of experience from our retail side with Amazon.com with the forecasting tool. And as you can see from the keynotes announcements, we're continuing to add tons and tons of features at this layer for AI services. But if we want to actually help machine learning get to the levels that we want it to be at, we realize we need to make developing your own machine learning models a little bit easier and more accessible. And that's why at that middle layer, we created Amazon SageMaker. Amazon SageMaker is a fully managed service that helps guide you every step of the machine learning development process, from labeling data, curating your data, building your models, and training them, deploying them, and everything in between. And again, as you saw yesterday, we are 2 days in Andy's keynote. There's a ton of new features and services that are around SageMaker, and it's hard for all of us to even keep up. There's so much advancement and innovation being done in that area, and so we'll continue to add more capabilities within SageMaker. And then at that final layer, the lower layer, we have the frameworks and infrastructure, and that's where we'll talk a little bit more about in this presentation. And we support all the major frameworks: TensorFlow, MXNet, PyTorch. And we actually have dedicated teams that are within AWS that are looking specifically at those frameworks, doing optimizations for a lot of the various models. So a lot of customers will come and say, we're using TensorFlow or PyTorch or MXNet, and our models aren't performing as well as we'd like. And so we'll have teams to help optimize. They know those frameworks inside out and help it run optimally on the AWS infrastructure. And if we move over to the actual infrastructure side, we've got a lot of different EC2 instances that I'll talk about as well in this presentation, and targeted specifically at machine learning. And we'll continue to add a lot of investments here as well. So if you look at our portfolio for accelerated compute, specifically for machine learning workloads, you may be wondering, what do I use for what? A lot of these times, you don't know the difference between different GPUs, and you don't know which one's better for which workloads. But there is somewhat of a clear distinction between training workloads and inference workloads. So just by show of hands, how many people are doing machine learning training specifically? And then contrast how many people are doing inference workloads. Okay, it's a decent balance. So if we think about the training side of it, really the P3 and P3 family are the primary vehicles for training workloads. These have the most compute performance, and as Maxim was talking about, this is where engineers want to experiment and iterate constantly. And we've built P3 and P3DN specifically to have the most compute performance and most powerful GPUs. We want your data scientists and your engineers to have high productivity. So if they're waiting around for models to train, I'm going to assume that your data scientists and ML practitioners cost a little bit more than what a P3 GPU would cost. And so P3, P3DN, those are going to be the primary platforms for machine learning training. But having said that, we did recently announce G4, which about a month and a half ago. And these actually were really targeted for inference workloads, but after doing some benchmarks and results for it, it actually turns out to be fairly cost-effective for certain types of model training. So these are smaller models where maybe you don't care as much about time to train. You're a little bit more flexible on that side. It does actually become a little bit more cost-effective for certain model types, such as vision models where you don't need super fast interconnects between servers and you don't need super large memory sizes. But for, if time to train is the most important thing, the P3s and P3DNs are going to be your best bet. And if we switch over to the inference side, by our estimates, the inference workload and cost of the inference workloads is that it makes up about 90% of the overall cost. And that's because if you think about it, training you do less frequently, maybe once or twice a week or once a month, whereas inference is happening constantly. There's constantly predictions happening, and that's more of your steady state workloads. And so this is the area where we wanted to provide some additional investment and make better products for you guys. Previously, we had primarily GPU instances and even CPU instances were used a lot for inference. And so that's why we introduced G4 to improve on the inference workloads, got better performance, better latency, and lowering the cost of inference compared to older GPU platforms like the P2. And then beyond that, if we felt like there was still improvement that could be made. And so we actually designed our own custom accelerator called Inferentia. And we built an instance around it called the Inf1 instances. And anytime you build a special purpose accelerator, you're going to get better performance, better power efficiency, and all the cost savings that we incurred on the infrastructure side, we're actually passing that on to our customers through the instance pricing. And so with Inf1, we're actually able to get the lowest cost per inference in the cloud. Very high throughput, very low latency. And there's this notion of we want to build the right tool for the right job. We don't just want one GPU platform to serve every kind of machine learning workload. We're going to continue to add different types of platforms for specific use cases. So we're in Vegas. If I were a betting man, I would say this portfolio of ML compute instances will probably grow this time next year. So if we focus specifically on the P3 and P3DN instances, we launched P3 in October 2017. We're actually the first in the cloud to offer these GPUs. And then last year at reInvent, we launched the P3DNs. And both of these instances are still really the gold standard when it comes to machine learning training platforms. If you look at the latest ML-Perf results, which is kind of the go-to for benchmark results of these ML workloads, the V100 GPUs are at or near the top across all the various model types, and more importantly, across all the different frameworks. There could be other training platforms out there that are specific to certain model types or specific to certain frameworks, but the P3 and P3DNs are very flexible across all of them. They're also available in 14 different regions around the world. So it's important that to a lot of our customers to have the compute local to where their data resides, so whatever country they're in. Transferring large amounts of data is not fun and can be cost prohibitive. And there could be data sovereignty preferences for certain countries. So it was important to us to make sure that we had wide availability of these instances around the world. And so if we look at the actual hardware of P3s, We have 8 of these V100 GPUs in a single server. And so we're actually able to get 1 petaflop of compute from a single instance size. That's the most you'll find across all of EC2. The other important thing with the P3s is they have very fast GPU memory. So there's a lot of data transfer between the GPU and the GPU memory. And so these have a special high bandwidth memory that offers 900 gigabytes per second. So very fast transfer between the GPU memory and the GPU. The other important thing is these have a very fast GPU to GPU interconnect. So prior to P3, like for P2, for instance, for a GPU to talk to another GPU, it actually had to go over the PCI Express bus to the CPU and then back down to the other GPU over PCI Express. And it's latency and it's much slower bandwidth than what NVIDIA created called NVLink. And that offers actually 300 gigabytes per second and direct connections between the GPUs. So with training workloads, the all-reduce function, there's a lot of GPU to GPU communication. And so that link is actually pretty important. And then the other thing that a lot of customers were talking about, within a server, it was about as fast as it could be. But when you go to more than one server, that interconnect between servers was actually the bottleneck. And Maxim talked about that with our various technologies and their clusters as well, that server-to-server interconnect became very important. And so that's why we introduced the P3DNs. These have 4 times the networking throughput, up to 100 gigabits per second. So that really kind of opened up multi-node training. And then the other important thing we added on that was EFA, which I'll talk about a little bit later in this presentation. So the key difference between P3 and P3DN, the GPU memory. So if you need large data sets, large model sizes, larger batch sizes, that doubling of GPU memory becomes important. And then if you want to do the multi-node training, that's where P3DN really shines. There are a few other improvements we made on P3DN. So we actually updated the CPU. So we went from a Broadwell class Intel CPU to a Skylake processor. So you get a few more CPU cores. You also get the AVX 512 instruction set, which was actually important for a few customers that are doing image classification model training, where the images needed to be resized, rotated, cropped, and a lot of that pre-processing work can be accelerated with the AVX 512 instruction set. So what's really driving the need for large-scale, multi-node distributed training? If you look at some of the model sizes and the trends that we're seeing in terms of model complexity, it's going up and to the right. And it's a fast-changing landscape. There are new papers and new models being introduced regularly within the machine learning community. And so we're seeing a need for this advanced infrastructure to help keep up with the compute needs. Right? And so you see ResNet 50 kind of towards the end. That for a long time, that was kind of the go-to model to really stress test the compute performance of your training platform. But you can see that's at the very far left. And at 26 million parameters, it kind of is pretty small compared to some of the newer language processing models. So with BERT, introduced last year, that really represented a pretty big increase in complexity and compute requirements for training that model. It's warranted. It's the state of the art in terms of language understanding. It really kind of opened a lot of eyes in terms of what was possible in terms of natural language understanding. And people are doing variations of BERT as well. Our friends at Facebook created something called Roberta, which is a variant of BERT that really increases the amount of data. But with that comes increased compute requirements. Right? And so, unless you have 1,000 GPUs and a whole day to train, it's going to be tough to train Roberta. And even at the far extreme, there are models like GPT-2, which really increases the amount of parameters and subsequently the amount of GPU requirements. So these are some of the trends we're seeing in the machine learning model complexity and why we're investing in building out our infrastructure to support that. So if you look at just the P3, a single P3 instance, 8 V100 GPUs, we're able to get reasonable training times for some of the standard models around object detection, some of the more primitive language translation models and image recognition models. But one interesting thing is just the hardware isn't the whole story, right? So the same hardware, 8 V100 GPUs, a couple of years ago, took about 8 hours to train ResNet 50. And then now it's under 2 hours, so with the same exact hardware. And that's from the optimizations we do in the framework level, at the model level, and the entire software stack. So we'll continue to improve on how we optimize these models. But then when we go to models like BERT, we're seeing huge increases in the amount of time it takes, from minutes and hours to now days and days. So that becomes very challenging, right? We don't want your data scientists and engineers to just sit around waiting for these models to train and make and make changes and iterations on the model. It takes a week and a half to do that. So that's why with P3DN and EFA technology, we're able to scale to multiple GPUs. Whether it's you can see in the graph, we went from 8 GPUs in a single server to 64, 128, and beyond. And we're seeing huge improvements in the amount of time it takes to train. And then to really kind of push the envelope, we provisioned 2,048 GPUs and reduced that time down to an hour. And so that was really a lot of work in terms of different components around the compute, networking, and model optimization that helped us get to that record number. So underlying within that 100 gigabit networking is EFA, Elastic Fabric Adapter. And you can see actually on the previous slide, the TCP version, which is our ENA technology, versus EFA. And you can see there is a pretty significant improvement between those two technologies, and that's purely on the networking side and how we transmit packets. And so that's where we created EFA. We knew there were lots of these tightly coupled workloads, both on the HPC side and the machine learning side. And so we knew there needed to be a better protocol than TCP. And so we were able to get lower latency and higher throughput with this technology. So let's look at a little bit closer at how we do this. So at the core is the scalable, reliable datagram. So the way these packets are transmitted is a bit different than TCP. And we looked at some of the popular on-premises networking technologies like InfiniBand, but we knew that wouldn't exactly fit in our network infrastructure. We talk to customers a lot and understand how their applications work, and then we know how we design our networking infrastructure, and so we had to make some changes in terms of how to build this out. And one of the key pieces was the out-of-order delivery of packets. So we relaxed that packet delivery scheme, and so that as there's packet losses and the system was waiting for a particular packet to arrive, that caused slowdowns in the applications. And we know packet loss happens pretty regularly. And also, talking with customers, applications don't necessarily need to wait for a single packet a lot of times. And that out-of-order packet delivery was actually one of the key pieces that makes EFA work much faster and is much more resilient. Another key piece is multipath routing. So the way we design our network infrastructure is that between any two network nodes, there's actually multiple paths between those two nodes. And knowing that, we took advantage of that with the SRD protocol, in that we spray packets across all of these multiple paths. And that way we know that packets can arrive and we can reassemble them effectively without caring about a single packet that's being lost. And so this also helps with bandwidth as well. So by transmitting multiple packets at the same time across multiple paths, one, we're resilient against packet loss, and we're actually able to get better delivery and throughput due to this. And so here's kind of a side-by-side comparison of SRD versus TCP. So instead of a single stream of packets with TCP that need to be in a particular order, we send messages, and these can be out of order, and they can come at whenever they do come and be reassembled at the application level. We also have the ability to dynamically tune the timeout period. So instead of having a higher fixed period, we can dynamically adjust it at the microsecond level. And then, as I said, the end result is we can actually see up to 3x throughput improvement compared to TCP-based applications. So we'll switch gears a little bit to storage. With these large machine learning clusters, loading the data and providing enough data fast enough became a bottleneck at some point. And so, there are solutions out there that we provide EBS or EFS. Some of those just weren't quite up to the task of handling some of these very large machine learning clusters. And so, luckily, there was a product called FSx for Lustre that was announced last year that really helps provide a fully managed parallel file system. And there are a number of benefits with FSx for Lustre. Massively scalable performance. So as your cluster grows and scales, the amount of data you use scales. The performance also scales along with that. It's very easy to connect this to standard data repositories. S3 buckets is very common for people to store data into. This connects very easily to that. It can also connect to your on-premises data stores as well. It's very simple. Parallel file systems, typically, it's fairly complex to set up, but FSx for Lustre makes that much easier. It's very cost optimized in such that you use it only when you're actually running a workload, and you can shut it down if you're not using it. And in security compliance, that's always a key priority for us in all of our services. So on the performance side, we're actually able to get hundreds of gigabytes per second of throughput. And sub-second, millisecond latencies, and also support thousands and thousands of cores. As I said, it acts kind of as a caching layer between S3 and your compute clusters. And so as your processing results, that output can then also be synced back to S3 very easily. So now let's look at a lot of these pieces combined with the compute clusters in the center, right? And so you can be hundreds, thousands of GPUs using P3 and P3DNs. It has that very fast 100 gigabit networking interconnect with EFA technology in the case of P3DN. And another key piece that's shown in here is the idea around cluster placement groups. So by specifying your node as a cluster placement group, that actually provisions the resources all very close to each other, a lot of times in the same room in the data center. That offers much better latency and also helps make sure that there's very fast connections between the nodes. In a lot of cases, we're actually able to see almost 20% improvement for some of these really large nodes by using cluster placement groups. We have our file system with FSx to provide data to all of the servers very quickly, very fast. And a lot of people use AWS Batch to manage these clusters. These clusters can get very big, and to auto scale and spin up and down these servers as needed, tools like AWS Batch are really great for that. And then lastly, containers are getting very, very popular with machine learning workloads. And so we're able to offer Elastic Kubernetes service and our Elastic Container services to work very closely on these kind of workloads and help manage your containers. So now we'll switch to the inference side. And Inferentia was announced last year, and then we made it generally available this year with the Inf1 instances. So we're able to see a ton of improvements in inference workloads from a performance standpoint, latency standpoint, and the cost to do inference. These also have the latest generation Intel processors and that 100 gigabit networking as well. And so you can see some of the typical use cases for inference that we'll be supporting on this, as well as supporting all the major frameworks. And to dive a little deeper into this, let's look at some of the performance numbers and cost numbers around Inferentia. So G4, we launched it just a month and a half ago. When we launched it, it was the best platform for inference that we had. Very high throughput, very low cost compared to what was out there at the time. But if we compare G4 versus the Inferentia instances, we're actually able to see about a 3x improvement in the throughput. And due to the cost savings that we're able to see, we're able to get 40% lower cost per inference using Inferentia. And this is with a BERT model that we're doing on TensorFlow. And so if you don't have strong dependencies on CUDA or TensorRT and some of the NVIDIA libraries, we really think Inferentia will be a great option for inference workloads. And then on G4, we still see a lot of great advantages to G4, and we have a lot of customers that are really excited about G4. And one particular area that we did a little bit different on G4 is in the sizing. We actually got some people that were a little confused on how the sizing worked. And so customers were telling us, we want a single GPU, but we want just a tiny bit of CPU and memory. And then other customers would say, we want a single GPU and a lot of, or single GPU and a lot of CPU and a lot of memory. Previous GPU-based platforms did not really offer that flexibility. You got one GPU and a set amount of CPU memory, and then you just double that and double that to get the various sizes. But with G4, we actually have 5 different sizes, all with a single GPU. And so that really helps people optimize exactly what they need and get the exact amount of compute that they need for their particular workload. And we do also have multi-GPU sizes as well. So G4, a very versatile platform in terms of not only machine learning workloads, but graphics rendering workloads and some of the HPC type workloads. And a great way to take advantage of G4 is leveraging the content that NVIDIA is coming out with. And so a popular SDK that NVIDIA has is called DeepStream. And this is for intelligent video analytics, right? So, and if you look at a lot of the standard video analytics workloads, they all have a lot of the same blocks, right? So the video is encoded, it needs to be decoded, or vice versa. A lot of times with the images, they need to be pre-processed. Like, as I said, cropping, rotation, resizing, and then the actual inference piece as well. So DeepStream helps make that much easier. It provides a lot of the core building blocks for these various functions and makes that much simpler to do. Included in the DeepStream SDK is actually an example shown here around vehicle detection. So this example shows detection of the vehicles. It draws a bounding box around it. And not only does it detect the vehicle, it will also detect the make of the vehicle, whether it's a Honda or Mercedes or Toyota. It will detect the color and also the type of the vehicle. So whether it's a car, SUV, a truck. And so all that is done on a single GPU within the G4 instance. And you can see some of the performance results there. So using H.264, we're able to see over 30 streams simultaneously of 1080p resolution, 30 frames per second. And almost double that once you go to H.265. And in both cases, there is actually still GPU utilization that's left for other processing tasks. So we have a great relationship with NVIDIA, and we have a lot of the support for their various SDKs with our GPU platforms. And with that, this slide is over now. Maxim and I will be around for questions, and so please come up and talk to us. We want to thank you guys for coming, and I hope this was useful for you guys. We also have some stickers, a small amount of stickers. If you guys want to come up and talk to us, we can try to hand those out. But thank you guys for coming.